So I have the pleasure to introduce Professor Dr. Gwen O'Sullivan, who is currently at Mount Royal University. Gwen's specialty is really environmental chemistry and environmental forensics. And many of you know that the workshop was originally hosted in Toronto, Canada at the Ministry of Environment. And Gwen was one of the people who was really there at the forefront of the MDCW in the very early days. So it's really a pleasure for us to have her here today, and I know that you'll enjoy her talk very much.
Thank you. Let's start sharing. Does this pointer work? It does. Sweet. Found it. Thank you very much for the kind introduction. I feel very small behind here. Maybe I'm going to move over a tiny bit. You know. I love this conference. I love coming here. I love the atmosphere it's created, and I really appreciate you guys, all the work that it takes to put it together. I know how much hard work that is, and I think everyone here probably really appreciates the time and effort and commitment for it. And I look forward to it every year, so thank you for that. I also want to thank all my colleagues, collaborators, the people I work with. I've been really fortunate. I work at a small undergraduate university, and I really jumped on the tailcoats of COURTROOM up there, who had the vision and enthusiasm to push for multidimensional chromatography, and also to Eric and Ralph, who back in those early days would allow us to go into the lab and run batches of samples so that we could generate data to show to our clients. So, you know, all those things are really, really important to be able to give us the access to things. And I was really fortunate as well that my university, you know, in the early stages as they transitioned to university, supported me in my crazy idea about purchasing a GC and allowed me to support, you know, provide the money once I paid it back. And that was a very stressful couple of years when I wondered whether I was going to make it back or not. But I'm still here, and now I've got 2 GCs, so it worked out. So that's amazing. And I've also been really fortunate to work with people in the wildfire management branch in Alberta and Freeport, who's really, you know, they've been doing the work for a long time, and they're interested and really enthusiastic about pushing the science forward. And that's a really special thing to have, and people that you work with are really prepared to go out on the limb to be able to help you help them solve a problem, which is amazing. And then, of course, I've got some amazing people in the environmental forensics and ARSON lab that I work in, like Kevin and some of my other students who just make the place I work in a really beautiful place to go to work every day. So, a long thank you, but I'm a bit worried my slides, I haven't got enough, so I have to go back. Okay, so what I'm going to talk about today is basically wildfire, and of course I can't help but also talk a little bit about structural fires and those kind of things for the context of it, because the work that we do in the lab, it could be analysing wildfire, wildland fire samples, but could also be looking at structural fire for the police or the RCMP or insurance agencies or investigators. So it's a really exciting field to be working in, but this is where I work. So I work in Alberta, which is this province here. And if you were to look at this kind of image, and the reason I provided this was to look at the potential of, you know, where fire can occur and how bad the fire can be. And I'm sure everyone in the audience here has sat in a city or in an office or in a dwelling and had that awkward feeling where your eyes are slightly watering from the smoke caused from wildfire smokes when you're sitting in your homes. I don't know how many people experience that. Yeah, and it's getting more frequent, and I guess that's an important thing, because a lot of the times we create images and maps like these because we're looking at management of things and how do we stop things or prevent things from happening, and that's important. So when we're looking at where it is that there could be a really high risk for fires, you can see, you know, obviously in the tundra up here, there's not a lot of material up there, so there aren't a lot of fires. As you progress, you've got larger forested areas here, and then as you go through the prairies, you've got grasslands, and so you can think about like where fires could actually occur and why they occur. And if you put that in the context of wildfires versus structural fires, you've kind of got 2 different scenarios in terms of that. You can also look at it in terms of the scales of things. I don't know why I put it on this side actually. On the terms of the scales of the fire. So this is a map that shows all the fires from 1980 to 2021. And these are large fires, so those things that were greater than 200 hectares. And as you can see, it matches up pretty nicely, actually, with the image that we saw before. So you can see the little red areas that were there. It showed about the higher danger risk. And then you can see, as it happens, there are fires here that are matching up with those ones. You can see some anomalies down here and along here. And that's generally related to the fact that we're mapping things related to 200 hectares. And we're putting it in terms of the scale and size of the fire. And so you're missing some of the areas here that are smaller in hectares. If you were kind of to reverse that map and map it in terms of the cost of the fire, it would have a totally different distribution to it in terms of like the liability and the risk associated. And if you were to map it again and look at it in terms of the health consequences for air quality, it would look totally different again. And that's something that's important to me when I think about like why we're doing this work and how the work moves through and forward in terms of like what questions we're asking and how we're answering those questions. One of the big components for answering these questions was originally derived by the cost of fighting fires. And so here's an example of how they plan out and budget the cost of managing of fires. And so the agencies come together, they look over several years about how much fire activity there was, and then they predict the severity of the fires, and then they think about how much it's going to cost to manage that. And of course, with things like climate change and changes in weather patterns and El Nino, La Nina, they can kind of predict how much it's going to cost. And so they have the values where it's the fixed cost and the variable cost and the total cost. And as you can see, the annual cost of fighting protection is kind of exceeding $1 billion for the last 10 years. $1 billion, that's quite a lot, and that's Canadian. So that's even bigger in American. On average, the cost has risen about 150 million per decade since the data was collected in the 1970s. So the costs are rising. And as someone mentioned yesterday, money is a driver. And I think that's something that's really important to consider about how we're managing and using the data that we're collecting. The other thing I don't want to forget about is wildland fires or wildfires are not the only types of fires that we encounter, and they're not the only thing that's expensive. So here's an example of a table that was generated from the Statistical Agency in Canada. And so you can look at the total number of incidents across from 2017 all the way over to 2021. And you can see the total fire incidences, there's a bit up and down here, in terms of numbers. But broadly speaking, it's in and around the 35,000 number of fires in a year. You can break that down into the number of structural fires, and then there's subdivisions here. And you can think about outdoor fires. So again, there's about 11,000 to 15,000 kind of fires, that would be considered wildland fires or wildfires every year. But there's an equal or larger amount of things that are called structural fires. And so if you think about how much it costs in the previous slide for a wildfire, if you think about the average cost of a structural fire is about $50,000, and you multiply that by each number of fire, you're talking about something that's close to $500 million a year just in structural fires. Is anyone surprised by that? No? I was really surprised actually about the cost of it. I don't know, it's a lot. And we don't hear a lot about it. So I think it's something that's really important to think about. For me, I was like, oh, that's a lot of money. I wonder where I could get some more research funding to help them address their question and look at it that way. So I don't know, maybe that was my bias to that. Other things to think about is like the type of structural fires, whether it's residential, industrial fires, those kind of things, and then vehicle fires and those ideas, and how we would look at those ones from an arson context, if that makes sense, because that's the kind of work that I do. So how do these things start? In Canada, about 2/3 of the fires, the wildland fires in Canada, are caused by people, and lightning causes the remaining third of those ones. That's a pretty broad country to say that, a third of them, but it depends where you are. So like in Western Canada, where we're situated, 50% of the fires are associated with lightning strikes, and 10% in the Maritimes are associated with lightning strikes. And that's just to do with the geography and the meteorological conditions that are there. And the big thing to think about it, though, is lightning does account for, even though it's a third, it does account for over 85% of the area that's burned. And that's something that's really important to think about. The reason why they also get really, really big is that the lightning strike will occur away from an urban environment. People don't see it as quickly, even though we've got really good monitoring systems. And so the fire spreads. And so those red dots that you saw earlier on, which are the fires that are over 200 hectares, it's because we didn't see them in time, and it's really hard to suppress them out in the boonies. And so they become really, really large fires. The smaller fires, though, those that are human caused, while they may not have a huge landmass burns, similar to the wildland fires, they are expensive, because what can happen is you can have property damage, cost of living damage, especially if they're grassland fires, looking at agricultural grounds, and obviously the bigger chance of loss of life. And so those things are something that's really, really important. So the human caused ones, obviously they make up 2/3 of the cost of them, or the causes of them. So like what kind of causes would those be? So I'm sure in North America you're very familiar with this bear, Smokey the bear. I wasn't as familiar with them in Ireland, but I'm familiar with them now. And so obviously those accidental causes, things like campfires, chains on your vehicles, parking in long grass, fire pits, those kind of things. And they are important because they're individually based causes. So, some fires that you might have large communities that are burnt might be an ATV vehicle, sparking that hasn't been cleaned properly. And then you might have a larger scale fire that might be associated with a train passing by, maybe maintenance work that's done on the track. And then, of course, in California, places like that, you have a lot of issues associated with the electrical network and sparking associated with that. So when you think about those human-caused fires, and you're an investigator, I guess the challenge is to think about what is the ignition and the fuel that's caused to create those ones, and how would investigating each one of those fires be different, if that makes sense. And so that's something to think about when you're investigating those ones. We do also have police-related arson. So those are fire-related homicides. And so there's a report out that NR can do for everybody that looks at the distribution of those ones. So, here's an example of if you're looking at property arson versus violent arson. So the number of property arsons per 100,000 versus the number of violent arsons per 100,000. And you can see obviously the property arson is larger than the violent arson. And so that's something to think about. You can also think that by context. So in rural areas in the north of Canada, you're 2.5 times higher than the rate in southern areas. And then that rate, again, is 4 times higher than those in urban areas. And so you start to think about the profile of the people that are lighting these fires and the rationale and reason for why they're lighting those ones. And that's something that's really important to think about when we're looking at investigating things. You can also think about how that's relevant for solving cases. Obviously, violent crime cases have a much higher success rate of going to court. Around 85% of those cases are brought to court and prosecuted, whereas those property ones and wildland ones, way lower than that. Less than 20% of those cases are ever convicted or brought to court. And so that's a big challenge when you think about the implications that has for reducing the number of fires that occur. So thinking about the work that we do, the work that I do, it's so diverse. Court might call me up and say, hey, there's a project that's coming in like 24 hours. How much is that going to cost, and can you do it? And I'm like, of course I can. I never say no. Learn to say no. I'm kidding. It might be something like where someone is using an incendiary device and has popped through the window of somebody's house, and they've used a Molotov cocktail, and then we're collecting samples of furniture and debris and those kind of things. It could be a fire case from a train, potential train situation where a train might have a forest fire. It could be, a wide variety of things. You might have fuel that's in the back of a car, and they're trying to determine and link that to somebody who's potential suspect at a fire in another location. So the diversity of it is really high. But I guess the question is really quite similar. The scale is huge, but the idea behind it. So these are two kind of examples. I have not worked on these cases. That's why they're up there. Hypothetical. These are two examples. So, for instance, there were 5 youths between the ages of 12 and 15. They were arrested because they set a fire near their school. Who hasn't thought about doing that? So this one is in Grand Rapids, which is in Manitoba. And so that's one of those cases where, I think they had got mad at their teacher or whatever, and it got out of shape, and there was some property damage done and potential for loss of life. Nothing, there was no loss of life, but they were arrested, which was a good thing. Then you might look at some other situations in BC where they have some cases over time. So this is an example, you can see the dates of them here, 2014, 16, 15, 14, and you can see all the different red dots represent where the fires were and the different timelines for those ones. And so there's a suggestion that looking at these fires, that actually this could be, I hate to use the word, a serial event, where one person could be setting those events over a time period. And so how would you investigate this versus this? And so how would that have implications for your analytical methods, your alignment, getting a sample in after a column change, all those things that are practicalities of it. And so that is something that's really important. They have put up a task force together to help identify the persons responsible for this wildfire, and I believe the cases are still open for that one. So that's something to think about. But it does show you how you might think about your sample size, what analytical approaches might be beneficial, and then how do you analyze samples, in 2017 and then in 2024 and determine if it was the same person or the same fuel. That makes you think about how you're setting up the investigation to begin with. Obviously, the end goal is to find if it is arson or not, and then to find out who the arsonist is, and then prosecute them. And this is tricky depending on where the fire setting is. So if you've got something in a rural wildland situation, or you have something that's property damage in an urban environment, the profile of those people can be significantly different. And so that is really driven by things like age, sex, their motivation, their employment, and their mental health. And then it's interesting to think about like things like wildland fires are typically set over a weekend. So about 60% of them are set either on 33% on a Saturday or Sunday, so 60% of them all together, usually between 6 p.m. and 6 a.m. And then in the summer months, 60% of them occur between April and September. So if you're setting a wildland fire or a wildfire, you don't want to be seen in the daytime. You don't really want to be cold. And so I really think I'm going to give you a clue for when most of your fires will occur. However, in urban and rural environments, those ones are most exclusively done, not by men. So I guess most wildland fires, most wildland fires are set by men that are aged between 18 and 30. I don't want to broad stroke that, but that's kind of what they're finding out right now with that. However, urban fires, about 30% of them are set by women, and most of them are motivated by revenge and things like that, and are closely tied to mental health for those situations. And so it is interesting to think about urban environment, when a fire is set in an urban environment is typically happening in the winter, and what the collaboration between mental health and winter conditions and motivations for that one versus something like a wildland fire, which is set in the summer when it's warm and generally with no intent for murder. For wildland fires, they're typically not sent to kill but to damage, if that makes sense. Okay, so I think we've now established what kind of fires we have, why we want to look at them, and so how do we go about doing that? So how do we go from the origin to courtroom? And that's something that's really important, obviously. So if you think about a situation with the wildfire, you're looking at a scene that looks similar to something like this. But the scale of it is just ginormous. And so you think about the motivation for what the forensic practitioner is doing. They're trying to find the area of origin, and then they're trying to find the primary fuel and the primary ignition source for that one in a massive environment. And so what happens is the investigator goes out. This is actually a picture of Court here. Those overalls look really clean, actually, Court. Did you just arrive on site? You're posing, yeah. And so they go outside and they look at the situation, and it's a vast scale. And so obviously they'll look at other factors, like weather conditions, where eyewitness statements, those kind of things to determine where they might start to narrow down the area of origin. And then the canine units. I don't have many dog pictures, but I wish I did. Your video was adorable. They're an amazing set of people, and the handlers that use the dogs, and the dogs are incredible. They go out and they start to work the scene, and then they determine where they can smell the accelerant, the ignitable liquid residue, and then the investigator marks those locations, and then the investigator will actually pick the samples up from those locations. So you can see here, there's an overview, the dog goes out, they flag a site, and then the investigator has to take a sample at those locations. And so, dogs are amazing. Like I don't know if you've heard of this one. Some of the phrases like, if you put a teaspoon of sugar into 2 Olympic-sized swimming pools, they'd still be able to smell it. That kind of scale, like it's absolutely incredible. The challenge is being able to use that evidence in court. So we do have to try and match the dog. So the sampler will have some biases because the dog's not put the flag down. The dog's marked the location. And the sampler is the investigators to mark the flag, the handlers to mark the flag, then the investigator comes in and decides where in that little area to take the sample. And so you can start to see we're already facing a challenge with collecting trace levels of an ignitable liquid in a really complicated, crazy scene, if that makes sense. And so we're assuming the dog's marked it, the handlers point the flag down really nicely, and then the investigator has taken the sample right where the dog was, and that has now encompassed the ignitable liquid residue from that location. You're in the middle of, I keep saying boonies, but I don't know what you would call it, in the middle of nowhere, and you have to ship those samples back. You have probably 2 to 3 more days still on site, and then you ship them back to the lab, they get to the lab, and then you have to analyze them. So you can start to think about the time frame, the conditions that can occur in between the sampling and then the liquid gets to the lab. You get to the lab, you basically put a carbon strip into the top of the headspace, you collect it, heat it up to temperature, and then all the ignitable liquid residues move to the carbon strip. You desorb the carbon strip with carbon disulfide, and then you inject it onto an instrumentation. The method for ASTM will suggest it's a GCMS. And so you can see there's quite a few steps here. And I guess the objective really is to determine for the investigators, they're trying to determine the area of origin. They assume they've got that with the dog and the other pieces. Now that they're determining the presence or absence of an ignitable liquid residue. And so we're trying to determine and build up the lines of evidence. As you can imagine, the minute the fuel was collected from the pump, it's evaporating and weathering. You're like at a fighting battle. The scene itself, if we look at it like this scenario here, it's vast. It gets huge, and it's obviously been suppressed. So, obviously it either burnt all out, or we've used water from airplanes and bombers, that kind of thing. And you're then trying to find the equivalent of a needle in a haystack. So it is really, really challenging. You also have things like low levels of ignitable liquid residues. So, the residue that hasn't been burnt, and you've got high levels of natural compounds, if that makes sense. And so the role of the investigator is to gather the information, to bring it to court, to articulate that, without doubt, this is a scenario where arson occurred, and you're building up lines of evidence to say this person was responsible. I don't know how many people have been to court to testify. It's something that gives me a cold sweat. And to be honest with you, the thought of that, because we talked yesterday about working with our students, and they weren't going to do dentistry, now they're going to do GCGC. I don't know if they're still here. That gave me cold sweats. I was thinking, my goodness, dentistry. But those kind of things, when you think about the scale of this too, you're changing the trajectory of people's lives, and so you have to be confident about that one. And so that's something that's really important, and we haven't always done it well, which is a fact, right? There's a huge amount of uncertainty in any types of the analysis, and so if we think about the history of how we've done this, we think about the training and the qualifications of the field investigators. So, we've been doing structured arson investigations since about the late 1940s. And really the training that was required before 1991, 1992, you did like maybe 48 hours of training, and then you got all of your training experience on the job, where you were experiencing fires and looking at fires and trying to determine what happened. And that foundation was pretty rocky, and a lot of people went to prison, and some people were executed for a crime that they did not actually commit, based on the fact that the scene was interpreted incorrectly. So it wasn't actually arson. So things like alligator patterns, breaking glass, depressions in furniture, they found it hard to predict where the area of the origin was, which meant that they weren't actually sampling in the right location. So they were using visual indications to determine that it was arson, and in fact it wasn't arson at all. And so, they started to realize this, in 2000, 2009, after one poor soul in the US was executed in 2009 and was wrongly convicted of that one. And a lot of work was done then to start thinking about how are we going to correct these ones. So, even in the 90s, which is the first time the National Fire Protection Association created a guidebook for that, and which is now considered the Bible for it. That was the first one in 1992, and they created iterations from that. The challenge was they had the guidebook, but people were finding it difficult to be able to leave go of the previous methods. Sound familiar to anybody? And so, all the years that you've been doing something a certain way had to change, and that is very, very challenging. I mean, I find it challenging changing from like my Apple phone from 2010 to my flip phone. Those kind of things are really challenging. But think about it on a greater scale when you're interpreting a field investigation. It's really hard. ASTM has created some methods. So those ones started in 1997. And, there are some advantages to those ones because they provide structure. There are also some disadvantages because it brings with it an ideology that things must be this way. And we don't all have to use those ASTM standards. So in Canada, we follow them, but we have flexibility to determine an appropriate method to use it as an alternative. And so that can be, it can be a little bit, it would be really helpful as a structure, but it's also a little bit debilitating when you're trying to investigate something, a particular research question. The Forensic Science Assessments, they did a quality gap analysis in 2017, so the American Association for Advancement of Science, and they started to look at knowledge gaps that were associated with the investigations. And so that's really the first time we were thinking, okay, look, we know it's not right, we have some structure, but could we start to identify some areas where we could develop research questions and support the academic community to be able to address those ones, if that makes sense. And so that's really the start of a rapid change. The standard method that we're using, as I mentioned, is the ASTM method. I am getting to GCGC, I promise. And so these are some examples of how you can look at different, single line modes, and you're basically looking at a visual representation, trying to find examples of things like the C2 benzene, so the Three Musketeers, the Casa group, the Gang of Four, Five Fingers, and Twin Towers, and you're literally, putting it up to the light and looking for the shapes basically for those ones. They must be present for it to be effective. The challenge with this is that we're in a wildfire debris matrix, and sometimes the ILRs are present at concentrations that are way below the matrix, and so it becomes really challenging to be able to separate out those compounds. So initially we were looking at a study that was done with Court and Kate in their group, looking at the use of GCGC to kind of show the advantages of it. So if you look at here, we've got some other grey compounds of the other compounds. We've got the blue ones, which are the Stouffer compounds in the previous slide. and we've got the green ones, which are the natural compounds. And again, similar to what was said yesterday, if you were to compress it on this scale, you can see that these green ones are in places that are really awkward for blocking out the castle group, blocking out the other pieces of it, blocking out the twin towers. And so you can start to see that there's a lot of interference that could be associated with these natural products that are preventing you from seeing the ILRs, which means you're getting a lot, the dog has smelt it, but we're getting a lot of false positives, false negatives, which is a real challenge for investigations. So what we did is we wanted to look at creating a method for GCMS, or GCGC, sorry, to be able to, guide people through a structured process. So, we're going to say we're just going to use this new method without any validation or work in it. So, Nadine, who worked with me and doing her PhD, she's just nearly finished actually. She started to do a method development work. So, looking at using design of experimentation, so things like Box, Benken, and Doolert, to try to basically develop a method that was optimized for ignitable liquid residues in a fire debris matrix, if that makes sense. And so to do that, there was a series of workflows that were set up, looking at column selection, modulator settings, parameter optimization. The things to consider were like selectivity, retention, sensitivity, flow rates, loop fills. You can see how crazy this would be. So design of experimentation was really good. We looked at 7 column combinations with different stationary phases and dimensions and orthogonality. And then we basically looked at them by assessing them using a target compound list from the ASTM. We looked at retention, resolution, peak shapes, as well as the overall peak capacity and area used from the chromatogram, because we wanted to use as much of the chromatogram as possible to be able to separate out from potential interferences. It was pretty, successful for us in terms of creating a method. We used a low polarity column, 5% in the first phase, and 50% in the second phase, very familiar to everybody. What you can see is we were able to separate out the target compounds from the interferences, and then starting to look at our key compound areas, so our alkanes, cycloalkanes, alkenes, aromatics, and that kind of area. We tested it with a fire debris sample, which is this one here, and we applied it using the ASTM method, and it was very successful in terms of being able to tease out the samples. So we looked at positives and some previous false negatives and explored it, and so the method was pretty robust. You can see how we were able to separate out some of the interferences from the other target compounds. Here's an example of limonene here from these two, and carval here from the other one. So we were pretty happy altogether with the method developed for it. And so we've been using that method, variations of that method, as we progress through from 2017 to now, which is pretty good. However, we had the similar problems where we're, running a series of sets of samples, maybe 30 samples here and 30 samples there, and then doing routine maintenance or getting optimized and then running it again and realizing that we were having that alignment and shift and all those pieces. And so it was becoming very challenging to be able to compare old case samples with new case samples. And so what we wanted to look at is developing retention time indices for that. So we applied the COVATS indices and the Lee indices. So COVATS in the first and Lee in the second to develop 2-dimensional retention time indices. The benefit of doing that was that we were able to use alkanes and then our rings structures on the second dimension to be able to create a retention time indices. It fit really well when we ran them with the model than expected. And so the method, we compared it with the previous method that was set up using glycols, which wasn't particularly useful for our applications. And so it became really, really helpful for us. And so we now inject that mixture that we created into every sample so that we can avoid the problems with alignment of those kind of pieces. We were then able to take the retention time indices and use the STM to map it. So we can now use this map to lay out our ignitable liquid residues, where we can see the zones here. This is basically gasoline. This is petroleum distillate. Anything below here is going to be an isoparaffin, a naphthenic paraffinic product. And anything above here is going to be an aromatic product. And then we've got our oxygenates over here. And so we can lay our samples out on those ones. So this is an example. I know, really small, I'm sorry. Is an example of a gasoline falling within the gasoline range. And this is an example of a diesel or petroleum distillate falling in, where you can see the light components of it and then the heavier components of it. So it has been really effective for us to be able to plot our samples on there and start to look at our ASTM classes as we've gone. So that's kind of our method set up using our retention time indices so that we're confident that we're analyzing it in the right way. We then started to look at how we could apply it to look at exploring issues with cross-contamination and some other pieces. So this is an example of a glove box study that we did, where we were trying to look at the crosstalk or the cross-contamination of samples as they were transported from the field into the lab. And so that was something that was really useful for us. So we set it up using gravel, soil, and then burnt wood matrix. And so we looked at things in the background levels. So you can find, obviously, in gravel, there's nothing. In the soil, you've got different backgrounds. So here you can see the blue is your alkanes, your orange is your alkylated aromatics, your indines, and then these ones are your condensed ringed aromatics. And so you can start to see that the importance of taking a background sample so that you can actually compare your background sample, because if you just have your ILR impacted matrix, you start to get a lot of confusion about potential material that could be present in your sample already. And so we could see after 8 to 24 hours, most of the samples had been contaminated enough that they would be determined as a false positive, if that makes sense. A lot of the times it followed, it's the physical and chemistry of the sample. So like anything, obviously, with your Henry's law constant, your optimal water coefficient, you would predict a certain behavior, and that was valid except for some of the heavier ones when you can't use things like line wires for the interactions between the matrix and the chemical itself. That was causing some issues there, but they modeled it. The final distribution of the spike samples was similar for all of them, whether it was a gravel or a wood or a soil, and that was something that was interesting. However, the variation occurred as you were going through it, so depending on when your cross-contamination came in, I think the challenge is if you're interpreting the data, you need to be aware of what the profile would look like in various stages as it's cross-contaminated, if that makes sense, to avoid the potential of a false positive. And then we obviously use that data to be able to help us because we don't want to cross-contaminate our samples, and so we did additional study looking at different ways of packaging our containers to be able to avoid that. So we use the standard packaging methods that were used to help our investigators. I don't know how many of you have been to the field and it's freezing cold and you're trying to package metal cans in a plastic bag. It's not an enjoyable experience. And when you have to come back to the lab and unpack all that and then repack it in the same bag, it becomes a logistical nightmare and adds a lot of time to your work. Heaven forbid the soul-crushing nature of data interpretation. Think about the soul-crushing nature of unpacking and repacking these boxes. That's something that's important. And so we looked at the different types of packaging material, determined which one was the most effective. I think it's great to say, I think this method is really good. However, that really depends on the sample that you're collecting. So if I'm collecting a really sharp object that's 4 foot by 4 foot, a quart can is not going to be your jam. But what's important is to understand what would you expect to see in terms of interferences in the bag that you choose, so that you could better understand the quality of reduce the uncertainty of the data analysis. The other thing I wanted to look at was computational fingerprinting, and I don't have time today, which is unfortunate because I was really going to get into chemometrics, unfortunately, but I can't. So what we wanted to do was look at some of the challenges associated with, okay, we've got an lightable liquid residue. So that sample, that case I didn't tell you about where someone threw something in the window, what happened was there was a sink underneath it, and what they didn't realize was the U-bend was collecting the liquid that they were throwing in there. And so then could we possibly match that liquid with the can that was found in the back of their vehicle? That sounds really easy, but actually it's really challenging because you have to think about weathering and the influence of water, evaporation, all those things. And so we wanted to look at how we could develop some libraries and some databases to be able to manage those kind of scenarios. And so we did a case study in Calgary, when we looked at collecting samples from gas stations from different manufacturers. There's about 7 different producers that produce gasoline, I guess, in Canada, and then various different suppliers that add different additives. And so we were looking at the implications of additives in spring, summer, and winter, that kind of thing. And so we started with the first 30, and so the group working with Roxana Schuler in TMU and her student Huey, we set up a workflow. I won't go into the detail of it now because it's probably very similar to some of the ones that you've set up yourself, but maybe on a different platform. And so what's really interesting to think about this was how the implication is for what the question you're asking. And then that question has an implication for what data you're bringing into it. And so really we found that the pre-screening piece of it was so important because what we brought into our PCAs and our random forest and all those things was really impacted by what came in. I know that's like first year science, I know, but it's really hard to apply that when you're so excited about your data set. So I think putting in more time at the start, and we all know how hard it is to integrate and handle data, and so sometimes it can be really soul destroying. Have I mentioned that twice? To go back and reintegrate everything, and so that's the really thing, is to be really clear with what you're doing to begin with. And so very similar to everybody else, we've done some PCAs, and what we found really was that we were able to separate the gas stations down into groups. And we'll be adding in more of the data now as we go. So we actually probably have close to 200 samples, which we'll be adding in the next 6 months. And so hopefully for the age next year, we'll be presenting just this one and getting a regular one. Okay. The ongoing work that we're doing, which I think is really interesting, is we're developing an ILR reference library, but we're also including things that traditional accelerants, gasoline and diesel, are 2 of the most common ones. But as we've had more social unrest, Molotov cocktails actually are more commonly used now. And so we need to start looking at non-traditional accelerants. And so I spent a lot of time, you can imagine me driving around picking up this. How odd that must have looked when I was with my shopping trolley in Princess Auto. I don't know if you've seen that. Versus me going into Canadian Tire and purchasing everything that I could possibly burn. It was another experience. So when I went to the trolley, that was pretty good, which is really interesting. And so we're also looking at the implications. So those that's really important. So looking at the variations in the type of fuels we're looking. Also the implications for weathering. So what would it look like and how the patterns would change with weathering and modeling that one. And then the implication for extraction temperatures when looking at light versus heavy. And then also things like screening materials. So you're not going to believe this. The community is divided in two. Some think it's a really good opportunity to use something like GCGC. And other people think it's too powerful. It's too powerful because if we use it, we'll find more. And if we find more, it'll be harder to answer. So I guess it is true though, we will find more. But we might find that actually background levels are higher than we thought. And that maybe that case, that maybe that material when your shirt with the print on it did have some sort of hydrocarbon on it that was contributing to a positive signal. So it is true, we will find more, but I don't think we should stop because we'll find more. I think we should just answer those questions by looking at background concentrations and things. And so that's what we wanted to do in terms of looking at typical materials that are found in structural fires and wildland fires. And so we've done that work and we'll be integrating and posting that data this summer. And we've also done things like burn experiments where we have added accelerants to look at the complications from combustion and pyrolysis. And so, analyzing the sample, adding fuel, sampling it then, so looking at the retention of the sample and then burning it and looking at various times of retention. So that's other work that we'll be presenting hopefully next year as well. And I don't know if I've addressed any of the 5 things that you guys suggested I should talk about. But one of the things I wanted to talk about was new exciting areas. And so before I finish, which I know I'm 5 minutes over, is the potential for, using, and I know at the start, our hosts were indicating the use of GCGC for air monitoring. And it's a pretty exciting field now for wildfire forensics and human health issues, is connecting the use of unmanned air vehicles like drones to be able to air sample and then using those tools to be able to connect to GCGC to provide a really solid structure in terms of primary and secondary aerosols and the implications for health. And so keep your fingers crossed that I get the grant because we've got the drones and we're excited to do it. So that's our next step. So I don't know, my whole program will be filled for Liège, I think. But that's it. So I just want to say thank you for your patience for listening to me talk. I should have practiced it before I did it, but I was only writing it this morning. So there was a likelihood that would occur. But really what I want to emphasize is that there is a demand to increase the scientific rigor within fire investigations. There are natural hesitations to adopting those, but I think that's common to everybody. GCGC has, in our experience since 2017, decreased the number of false negatives in our work, and that's helping us to get better understanding of things like the implications of storage and preservations and weathering. And then obviously there's a huge potential for chemometric tools to provide support for fingerprinting sources. So I'm excited to talk to everyone in the room about processing and data management, because without the staffing and funding is one issue, but time for data processing is another. And I think those are important pieces for us to consider. And then thank you for your patience for listening to me.